Tonight we drift between galaxies, far beyond the familiar glow of the Milky Way, where the universe feels less like a place and more like an endless ocean of darkness. Ahead of you hangs a colossal spiral galaxy. Its arms sparkle with billions of stars, glowing clouds of gas, and scattered clusters of ancient suns. It looks complete. It looks understandable. If you had never studied astronomy, you might assume that everything important is right there in plain sight. But something is wrong. The galaxy is spinning. And it is spinning far too fast. You float silently beside it, watching the enormous spiral rotate through the black. By every ordinary expectation, the outer stars should be moving much more slowly than the inner ones. Gravity weakens with distance. The farther a star is from the galactic center, the less tightly it should be held. Yet that is not what happens. The distant stars race around the galaxy at nearly the same speed as those much closer in. If the visible matter were all that existed, these stars should have escaped long ago, flying off into intergalactic space like sparks from a spinning firework. Instead, they remain exactly where they are. Something unseen is holding them together. And that mystery will follow you through tonight's journey. Before we continue, a small request from your friendly guide through the abyss. Space contains black holes capable of swallowing entire stars, but apparently it still cannot consume the YouTube algorithm. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, feel free to comment your location and local time. It is always fascinating to imagine listeners scattered across one small world while we explore the largest things imaginable. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You continue drifting beside the galaxy. The stars shimmer quietly. Their light has traveled for millions of years just to reach this moment. Some of those stars were already shining before the first humans ever looked up and wondered what the night sky was. Yet almost everything that controls their motion appears to be invisible. This realization arrived gradually in human history. For centuries, astronomers believed that what they saw was largely what existed. Planets, stars, nebulae, and galaxies formed a universe that seemed observable, even if enormous. Then measurements became more precise. As telescopes improved, scientists began carefully studying how galaxies rotate. One of the most important discoveries emerged during the 20th century. When astronomers measured the speeds of stars orbiting within galaxies, they found results that simply refused to cooperate with expectations. The outer regions were moving too quickly. Again and again, galaxy after galaxy, the numbers kept pointing toward the same unsettling conclusion. Most of the mass was missing, or at least, most of the mass was hidden. This is an established scientific fact. The motions of galaxies indicate far more mass than can be accounted for by visible stars, gas, and dust alone. The universe seemed to be concealing something. As you watch the spiral galaxy before you, you begin to imagine what that hidden mass might look like. Perhaps enormous clouds, invisible planets, dark stars. Yet none of those ideas fully fit the observations. Whatever surrounds the galaxy appears to extend far beyond the bright spiral itself, forming an immense halo that cannot be directly seen. A gigantic, invisible structure, like the outline of a mountain revealed only by the way fog flows around it. The surprising observation is that everything you can see, the stars, planets, nebulae, black holes, and galaxies, accounts for only a small fraction of the universe's total contents. The familiar cosmos is not the majority. It is the minority. You are living inside the visible tip of something much larger. The galaxy slowly turns beneath you. One brilliant blue star flares near a spiral arm. A distant supernova briefly shines. Far beyond, countless other galaxies populate the darkness. Each one appears isolated. Yet appearances can be deceptive. What if these islands of light are connected by vast invisible structures stretching across unimaginable distances? What if the universe possesses a hidden architecture that your eyes cannot perceive? The idea sounds almost mythical. Yet modern astronomy increasingly suggests that reality may be stranger than many myths ever imagined. You glance toward a darker region beyond the galaxy's edge. Nothing appears there. No stars. No glowing clouds. Only blackness. And yet gravity seems to be present, working, pulling, shaping, influencing the motion of everything nearby. A force without a visible source. A shadow without an object. The deeper astronomers investigate, the more this unseen component appears everywhere. Around galaxies. Between galaxies. Across clusters containing thousands of galaxies. The invisible influence keeps reappearing like a cosmic fingerprint left at every crime scene. And that leaves us with tonight's first great question. What exactly is creating this hidden gravity? Is it some unknown particle? An undiscovered form of matter? A misunderstanding of gravity itself? Or is the universe hiding something even stranger than any of those possibilities? At this distance, the galaxy continues spinning peacefully, offering no answers. Only clues. The stars shine. The darkness remains silent. And somewhere within that silence lies one of the greatest mysteries in all of science. Most of the universe appears to exist beyond direct sight. You continue drifting forward, drawn by curiosity into deeper darkness, where the visible cosmos gradually gives way to the invisible one. The galaxy slowly fades behind you. Its bright spiral arms become a faint pinwheel in the distance, and soon even that glow dissolves into the wider tapestry of the cosmos. Around you stretches a vast landscape of galaxies scattered across unimaginable depths, like islands floating in a dark ocean whose shoreline can never be reached. You are still following the same mystery. The missing weight. The invisible mass. The strange gravitational presence that seems to accompany nearly every large structure in the universe. Yet before venturing deeper into the unknown, it helps to understand how humanity first learned to read the universe's clues. For most of history, the night sky looked deceptively simple. Ancient observers watched stars rise and set. They tracked planets wandering among constellations. They recorded eclipses, comets, and unusual celestial events. Many civilizations became remarkably skilled skywatchers. But the stars themselves remained distant points of light. No one knew their true nature. No one knew their distances, and certainly no one suspected that entire galaxies existed beyond our own. If you could visit an astronomer from 2,000 years ago and explain that the universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, you might receive a look suggesting that perhaps you had spent too much time staring directly at the sun, which, as a scientific strategy, has never been particularly recommended. The true scale of the cosmos emerged gradually. Telescopes revealed moons orbiting Jupiter, phases of Venus, and countless stars invisible to the naked eye. Over centuries, astronomy transformed from skywatching into a precise science. Then came a revolutionary realization. The fuzzy patches known as spiral nebulae were not clouds within our galaxy. They were galaxies themselves. Entire star systems far beyond the Milky Way. Suddenly the universe expanded. Not by a little, by an almost absurd amount. You drift through that expanded universe now. Every direction contains galaxies. Some spiral gracefully. Some collide. Some appear as giant glowing ellipses. Others stretch into bizarre shapes sculpted by gravitational encounters. Yet despite their diversity, many share the same mystery. Too much gravity. Too little visible matter. One of the first major clues appeared in studies of galaxy clusters. A galaxy cluster is a collection of galaxies bound together by gravity. Some contain hundreds or even thousands of members. Imagine standing on a hill and observing a swarm of bees. If the bees move too quickly, the swarm falls apart. The same principle applies to galaxies. Scientists can estimate the total mass of a cluster by measuring how rapidly its galaxies move. When these calculations were performed, the results were startling. The galaxies were moving as though enormous amounts of unseen mass existed throughout the cluster. The visible galaxies alone could not provide enough gravity. This was one of the earliest major hints that something hidden permeates the cosmos. An established scientific fact is that galaxy clusters contain far more gravitational mass than can be explained by visible matter alone. The discrepancy was not small. It was enormous. Imagine weighing a ship and discovering that most of its mass appears to be missing. Then imagine finding the same result for every ship in every harbor. At some point you stop blaming the scale. You begin questioning your understanding of reality. As decades passed, better observations strengthened the mystery. Radio telescopes mapped clouds of hydrogen gas. Optical telescopes charted stellar populations. Space observatories examined galaxies across multiple wavelengths. The conclusion remained stubbornly consistent. Visible matter could not explain what astronomers were seeing. The universe appeared heavier than it looked. You continue drifting through the darkness. Ahead lies a gathering of galaxies known as a cluster. Hundreds of brilliant systems orbit a common center. The view is breathtaking. Golden elliptical galaxies glow like lanterns. Blue spirals wind elegantly through space. Streams of hot gas fill the vast regions between them. Yet even all of this visible grandeur represents only part of the story. The surprising observation is that when astronomers create maps of mass using gravitational effects, the hidden component often dominates the visible one. The unseen outweighs the seen. The darkness outweighs the light. And strangely enough, gravity provides a way to detect it. According to Einstein's theory of general relativity, mass bends spacetime. Light traveling through curved spacetime changes direction. This effect is called gravitational lensing. You can picture it as a cosmic magnifying glass. When light from distant galaxies passes near a massive object, the light bends along curved paths. The background galaxies appear distorted, stretched, or duplicated. Sometimes they form arcs. Sometimes rings. Sometimes elaborate patterns that look almost artistic. These distortions allow astronomers to estimate where mass exists, even when that mass cannot be directly observed. You float beside one of these gravitational lenses. Behind a foreground cluster, distant galaxies appear warped into glowing crescents. It looks like reality itself has become soft and flexible. And in a sense it has. Spacetime bends. Light follows. Mass reveals itself. What makes these observations so remarkable is that the inferred mass often extends well beyond the visible galaxies. Invisible structures emerge from the calculations. Huge halos. Massive frameworks. ghostly scaffolding supporting the luminous universe. And this leads to an unsettling possibility. Perhaps galaxies are not the primary structures after all. Perhaps they are merely decorations attached to something larger and unseen, like frost outlining the branches of a tree on a winter morning. You cannot see the invisible framework directly, but you can see its effects. The cluster slowly recedes behind you. The distorted arcs of light fade into darkness. And as they disappear, another question begins to take shape. Suppose dark matter exists. Suppose these hidden halos truly surround galaxies and clusters. Then where did this mysterious substance come from? Was it present from the birth of the universe? Did it shape the formation of the first galaxies? Could the visible cosmos owe its existence to something that has never been directly detected? The answers remain uncertain. Yet every observation seems to point in the same direction. The universe is not merely populated by darkness. It may be built upon it. And somewhere ahead, beyond these clusters and galaxies, lie even larger structures waiting to reveal how deep the mystery truly goes. You continue forward through the darkness. The cluster of galaxies fades behind you, shrinking into a distant congregation of light. Ahead, the universe seems emptier at first glance. Vast black regions separate the luminous islands. The distances become difficult to imagine. Even light, moving at its impossible speed, requires millions or billions of years to cross many of these cosmic expanses. And yet the emptiness is deceptive. Something extraordinary begins to emerge. If you could zoom outward far enough, if your perspective expanded beyond individual galaxies and clusters, the universe would reveal a hidden pattern. Not randomness, not chaos, a structure, an immense structure. You drift farther away until entire clusters become tiny points. The cosmic landscape transforms before your eyes. Galaxies gather along gigantic filaments stretching across hundreds of millions of light years. These filaments intersect at crowded nodes where clusters form. Between them lie enormous voids, regions containing comparatively few galaxies. The result resembles a web. A cosmic web, one of the most astonishing discoveries in modern astronomy. An established scientific fact is that matter in the observable universe is distributed in large-scale filamentary structures often called the cosmic web. From this perspective, the universe looks almost biological, like neurons in a brain, like roots spreading through soil, like threads woven into an unimaginably vast fabric. The resemblance is only visual, of course. The cosmic web is not alive, at least as far as anyone knows. The paperwork on that question remains incomplete. You glide alongside one of these colossal filaments. Galaxies drift through it like luminous droplets within an invisible river. And that image is closer to reality than it first appears. For astronomers increasingly suspect that dark matter helped create this architecture. Long before galaxies formed, invisible matter may have gathered into dense regions under the influence of gravity. Ordinary matter, gas, plasma, and eventually stars, then flowed into those gravitational valleys. In other words, the visible universe may have assembled itself around a hidden framework, like cities developing along ancient river systems. The rivers guide the growth, even if they are not the buildings themselves. You imagine the young universe. Nearly 14 billion years ago, everything looks dramatically different. There are no galaxies, no planets, no stars. Only an expanding sea of hot plasma filling space. Tiny fluctuations exist within that early plasma. Slight differences in density appear from place to place. Most are incredibly small. Yet gravity is patient. Given enough time, even tiny differences can grow. A slightly denser region attracts more matter. That additional matter increases its gravity, which attracts still more matter. Over millions and billions of years, structures emerge. The surprising observation is that computer simulations reproduce the large-scale structure of the universe far more successfully when dark matter is included. Without it, many of the cosmic patterns astronomers observe become difficult to explain. With it, filamentary networks resembling the actual universe begin to appear. The match is not perfect. Science rarely offers perfection. But the resemblance is striking. You continue drifting through the filament. Everywhere, galaxies shine against the darkness. Some are ancient red giants where star formation has slowed. Others blaze with youthful blue stars. Collisions occur occasionally, though the vast distances between individual stars usually prevent direct stellar impacts. Galaxies merge. Black holes grow. New stars ignite. The cosmic web slowly evolves. Yet the invisible framework remains frustratingly elusive. You cannot photograph dark matter directly. It emits no detectable light. It does not appear to absorb or reflect electromagnetic radiation in ways that astronomers can easily observe. Instead, its presence must be inferred. Gravity becomes its signature. Motion becomes its fingerprint. Distortion becomes its calling card. You pass through a region where two galaxy clusters have collided. The aftermath is spectacular. Galaxies stream through one another. Hot gas clouds interact violently. Shockwaves ripple across millions of light years. Yet something even stranger appears in the observations. In several famous collisions, the visible gas and the inferred mass seem partially separated. The ordinary matter slows and interacts. The hidden mass appears to continue moving more freely. This has become one of the strongest pieces of evidence suggesting that dark matter may represent a genuine physical substance rather than simply a misunderstanding of gravity. The mystery deepens. Because if dark matter truly exists as matter, then what is it made of? Not atoms. At least not the familiar atoms that compose stars, planets, oceans, trees, and sleepy humans listening to bedtime stories. Astronomers know that ordinary atomic matter accounts for only a fraction of the universe's total contents. Most of reality seems to belong to categories that remain largely unknown. Imagine discovering that everything familiar, every mountain, cloud, animal, city, ocean, and star, constitutes only a small visible layer atop a much larger hidden world. It would feel unsettling, and perhaps a little humbling. You drift into one of the immense cosmic voids. The transition is gradual. Galaxies become rarer. Clusters disappear. Distances between luminous objects grow enormous. The darkness deepens. Here, the universe feels almost empty. Yet even these voids are not entirely vacant. Particles drift through them. Radiation crosses them. Gravity still operates. And dark matter may remain present even where visible matter is sparse. The silence becomes profound. No nearby stars. No glowing nebulae. Only the faint awareness that invisible structures continue extending far beyond sight. The scale is difficult to comprehend. A single galaxy is enormous. A cluster is vastly larger. A filament larger still. And the cosmic web spans much of the observable universe. You begin to appreciate that dark matter is not merely a local curiosity affecting a few galaxies. If current evidence is correct, It has influenced the growth of cosmic structure itself. It may have helped determine where galaxies formed, where clusters emerged, where stars eventually ignited. In a strange way, your own existence may depend upon an invisible substance that no one has yet directly identified. And that realization leads naturally to a new question. If dark matter shaped the universe from the beginning, then perhaps its origins reach all the way back to the birth of the cosmos itself. Perhaps the mystery is older than galaxies, older than stars, older even than the Milky Way. Somewhere ahead lies the story of those origins, and with it, the possibility that the invisible universe began influencing reality almost from the very first moments of time. The cosmic void gradually falls behind you. Ahead, galaxies begin to reappear, scattered at first, then gathering into larger communities connected by the vast filaments you have been following. The invisible framework seems almost tangible now, not because you can see it, but because its influence appears everywhere. You have traveled from spinning galaxies to giant clusters and across the cosmic web itself. At every scale, the same question persists. What exactly is creating all this hidden gravity? Tonight's journey has so far revealed the fingerprints of dark matter. Now you move closer to what astronomers call a dark halo. If a galaxy is the glowing city, the dark halo is the invisible landscape surrounding it. You approach another spiral galaxy. From a distance it looks familiar. Brilliant stars outline elegant arms. Dust lanes curve through the disk like rivers of shadow. Bright star-forming regions sparkle with newborn suns. Yet the visible galaxy occupies only a small portion of its total gravitational domain. Far beyond the glowing edge stretches an enormous halo of unseen mass. You cannot see it directly. No telescope has ever captured a simple photograph labeled, "Here is dark matter." Instead, scientists reconstruct its presence through careful measurements. The process resembles tracking an invisible animal through fresh snow. You never see the creature itself. You see footprints, broken branches, disturbed ground. Evidence accumulates. Eventually, the unseen becomes difficult to deny. An established scientific fact is that galaxies appear to be embedded within extensive dark matter halos whose mass greatly exceeds the mass of visible stars and gas. As you drift through the outer regions of this halo, nothing seems unusual. Space appears empty. The stars are far away. Darkness surrounds you. And yet gravity is everywhere. The galaxy's outer stars continue orbiting faster than expected. Satellite galaxies move through the halo. Gas clouds respond to gravitational forces that visible matter alone cannot explain. The invisible remains active. One of the most surprising aspects of dark matter is how little interaction it seems to have with ordinary matter beyond gravity. Imagine two ghosts passing through each other. That image is not scientifically precise, but it captures part of the mystery. Dark matter appears remarkably reluctant to interact through light. It does not glow. It does not shine. It does not appear to participate in the electromagnetic drama that makes stars, planets, and people visible. In a universe full of spectacular displays, dark matter behaves like the quiet guest who attends every gathering and never speaks. The cosmic introvert. Although even introverts usually leave more evidence behind than dark matter has so far. You continue deeper into the halo. The galaxy's bright disk now appears as a luminous island surrounded by an invisible ocean. And here another puzzle emerges. Theoretical models can successfully describe many dark matter effects on large scales. Yet when astronomers examine smaller scales, certain discrepancies appear. Some galaxies contain fewer satellite companions than expected. Others possess central regions whose density distributions differ from simple predictions. These issues remain areas of active research. Importantly, they do not necessarily invalidate dark matter. Instead, they remind scientists that understanding remains incomplete. Reality often turns out to be more complicated than initial models suggest. The universe has a habit of accepting our calculations and then politely informing us that additional homework will be required. You watch a small dwarf galaxy orbit its larger neighbor. These dwarf galaxies are among the most dark matter-dominated objects known. Some contain relatively few stars yet appear to possess substantial gravitational mass. In certain cases, the invisible component seems to outweigh the visible one by astonishing amounts. Imagine a tiny lantern hanging inside an enormous invisible castle. That is roughly how some dwarf galaxies appear. Their faint starlight reveals only a fraction of what may actually be present. The surprising observation is that some of the smallest galaxies provide some of the strongest evidence for dark matter's existence. One might expect the largest systems to offer the clearest clues. Instead, these modest galaxies often become important laboratories for studying the invisible universe. You continue onward. The halo extends much farther than intuition expects. This is one reason dark matter remains so difficult to visualize. Human experience evolved on a planet where objects generally reveal themselves through sight, sound, touch, or some combination of senses. Dark matter seems content to ignore those expectations. Its effects emerge primarily through gravity across enormous distances. The evidence becomes statistical, indirect, yet persistent, and persistence matters in science. A single anomaly can be dismissed. Many independent observations pointing toward the same conclusion demand attention. Galaxy rotations, cluster dynamics, gravitational lensing, cosmic structure formation. Each line of evidence arrives through different methods. Yet all seem to indicate that something unseen contributes substantial mass to the universe. Still, uncertainty remains. And uncertainty is where the mystery grows larger. Because dark matter's existence is strongly supported by observation, but its identity remains unknown. Scientists have proposed numerous possibilities. Some involve entirely new particles. Others suggest modifications to gravity. Still others explore ideas that blend aspects of both. Evidence helps narrow the field, but no definitive answer has emerged. Imagine discovering footprints across an entire continent while never finding the animal that made them. You would know something exists. You simply would not know what. As you drift beyond the halo, the galaxy shrinks behind you. Its invisible envelope stretches outward before gradually fading into the larger cosmic web. The darkness feels different now. Not empty. Occupied. Structured. Filled with hidden influences shaping the visible universe. And yet the mystery is beginning to evolve. Until now, dark matter has largely been a question of mass. Missing mass, invisible mass, hidden mass. But ahead lies another connection, one involving some of the most extreme objects in existence. Black holes. There, gravity reaches extraordinary intensities. There, spacetime itself bends dramatically. And there, some physicists suspect clues may exist that connect matter, information, and the deeper architecture of reality. The hidden universe may not simply surround galaxies. It may be woven into the fundamental structure of space and time themselves. And that possibility is stranger than anything encountered so far. The invisible halo fades into the distance. Ahead, a new darkness emerges. Not the gentle darkness between stars. Not the vast darkness of cosmic voids. This darkness feels different, deeper, heavier, as though space itself has been pulled inward and tied into a knot. You are approaching a black hole. At first, it appears surprisingly ordinary, or rather, surprisingly invisible. Contrary to popular illustrations, black holes do not resemble giant vacuum cleaners roaming the cosmos in search of victims. If our sun were magically replaced by a black hole of equal mass, Earth would continue orbiting almost exactly as it does now. It would become a very cold place, admittedly, but orbital mechanics would remain largely unchanged. The black hole would exert the same gravitational pull as any other object with the same mass. The difference emerges when matter ventures too close. As you drift nearer, stars behind the black hole begin to distort. Their light bends around it. The background universe appears warped. The effect is subtle at first, then dramatic. Einstein's theory of general relativity predicts that mass-curve spacetime and black holes represent some of the most extreme examples known. An established scientific fact is that black holes form regions where gravity becomes so intense that nothing crossing the event horizon can return. The event horizon. Even the name feels mysterious. You approach it slowly. No visible wall appears. No glowing boundary. No cosmic warning sign politely suggesting that visitors should remain behind the safety railing. The horizon exists as a mathematical boundary in spacetime. Cross it and every possible future path leads inward, away from the outside universe, toward the unknown. For now, you remain safely outside. The black hole before you is supermassive. Millions or perhaps billions of times more massive than the Sun. Such giants inhabit the centers of many galaxies, including the Milky Way. In fact, astronomers now believe that most large galaxies host central supermassive black holes, which is an unexpectedly dramatic feature for something hidden in the basement. You watch hot gas spiral inward. The material forms an accretion disk, a glowing whirlpool of matter heated to extraordinary temperatures. Friction and gravity transform motion into radiation. The disk blazes brilliantly. Ironically, some of the brightest regions in the universe can form around objects famous for being black. Space clearly enjoys irony. The closer you look, the more connections emerge between black holes and the mysteries you've already encountered. Dark matter appears to influence galaxy formation. Galaxies often contain supermassive black holes. Those black holes affect their host galaxies through powerful gravitational and energetic processes. The universe begins to resemble a vast interconnected system, not a collection of isolated puzzles, but overlapping mysteries woven together. You drift along the edge of the accretion disk. The light around you becomes increasingly distorted. Time itself behaves differently here. According to general relativity, gravity affects the passage of time. Clocks near strong gravitational fields run more slowly relative to clocks farther away. This is not science fiction. It is a measured reality. Even satellites orbiting Earth must account for relativistic effects to maintain accurate positioning systems. Near a black hole, those effects become extreme. The surprising observation is that time and gravity are intimately connected. Something as seemingly universal as the passage of seconds depends upon location. The cosmos does not provide one master clock ticking uniformly everywhere. Instead, time becomes part of the dynamic structure of spacetime itself. You imagine hovering near the event horizon while distant centuries pass elsewhere. Entire civilizations might rise and vanish. Stars could evolve. Galaxies could change. Meanwhile, your own clock would record far less elapsed time. The idea feels almost dreamlike. Yet it emerges naturally from equations that have repeatedly passed experimental tests. The black hole grows larger in your view. Its shadow dominates the surrounding stars. Light bends into strange arcs around its boundary. The universe appears stretched and twisted. And here the mystery deepens again. Because black holes create a profound problem involving information. In physics, information refers to the detailed description of a system, the arrangement of particles, their properties, their states. According to many fundamental principles, information should not simply vanish. Yet black holes seem capable of swallowing matter and hiding that information behind the event horizon. Then another discovery complicated matters further. In the 1970s, physicist Stephen Hawking showed that black holes are not completely black. Quantum effects imply that black holes can slowly emit radiation. This process is now called Hawking radiation. Over extraordinarily long timescales, a black hole could gradually lose mass and eventually evaporate. If that happens, what becomes of the information that fell inside? Does it disappear? Is it somehow encoded in the outgoing radiation? Does spacetime preserve it in ways not yet understood? This unresolved mystery remains one of the deepest questions in theoretical physics. The information paradox sits at the crossroads of gravity, quantum mechanics, and the nature of reality itself. You circle the black hole thoughtfully, or at least as thoughtfully as one can while orbiting a region capable of consuming stars. The event horizon remains silent. No answers emerge, only more questions. And strangely, those questions begin connecting back to dark matter. Both mysteries involve invisible components of reality. Both reveal limitations in current understanding. Both suggest that the universe possesses hidden layers beneath everyday observation. Scientists do not currently know whether dark matter and black holes share any fundamental connection beyond gravity. Most evidence treats them as distinct phenomena. Yet both stand as reminders that visible matter tells only part of the cosmic story. The deeper you investigate, the more unseen structures appear. Invisible mass, invisible horizons, invisible information. The universe seems determined to hide its most important secrets in darkness. As you drift away from the black hole, its distorted shadow slowly recedes behind you. Ahead lies an even broader frontier, the search for dark matter itself. The laboratories buried underground, the detectors waiting patiently, the elusive particles that may or may not exist. Humanity has found the footprints. Now comes the challenge of finding the creature that left them. And that hunt is one of the most fascinating scientific adventures ever undertaken. The black hole dwindles behind you. Its shadow merges once again with the greater darkness of space, leaving only memory and unanswered questions. Ahead, there are no glowing accretion disks, no warped rings of starlight, no obvious spectacles. The next stage of the journey is quieter, much quieter, because now you are following a hunt. One of the most ambitious hunts in scientific history. Humanity has spent decades searching for something that has never been directly seen. Not a lost city. Not a hidden planet. Not an undiscovered continent. An entirely unknown form of matter. You drift downward not toward a planet but toward an idea. Far below the surface of Earth, deep inside mountains and underground laboratories, detectors sit in darkness. The darkness is intentional. Scientists bury these instruments beneath rock to shield them from cosmic rays and other sources of interference. They are trying to create some of the quietest environments ever constructed. The goal is simple to describe and extraordinarily difficult to achieve. Catch dark matter in the act. If dark matter consists of particles moving through space, then trillions of them might be passing through your body right now. That statement sounds surprising because it clashes with ordinary intuition. Yet if dark matter fills our galaxy, then Earth should be moving through a vast cloud of it as it orbits the Milky Way. The particles, if they exist, would stream through planets, stars, and people with almost no interaction, like wind passing through a ghost. Or perhaps more accurately, like ghosts passing through ghosts. Physics occasionally develops a sense of humor. An established scientific fact is that many dark matter experiments attempt to detect rare interactions between hypothetical dark matter particles and ordinary matter. These detectors wait patiently. Years pass. Data accumulates. Researchers examine tiny signals that might reveal a new particle. So far, however, definitive detection remains elusive. And that is where the mystery becomes particularly interesting. Because scientists have many ideas. Too many, perhaps. The universe has supplied abundant clues but stubbornly refuses to provide the final answer. One popular class of candidates became known as WIMPs. Weakly interacting massive particles. The name sounds less like a revolutionary scientific concept and more like a group project partner who promises to help but never replies to messages. Yet for many years, WIMPs were among the leading possibilities. These hypothetical particles could naturally explain several observed properties of dark matter. Experiments searched for them extensively. Despite remarkable sensitivity, no confirmed detection has emerged. That does not mean WIMPs do not exist. It simply means nature has not yet provided the evidence scientists hope to find. As you drift onward, the search broadens. Another candidate appears. The axion. Unlike WIMPs, axions would be extraordinarily light. They emerge from theoretical attempts to solve other problems in particle physics, yet they could also contribute to dark matter. Laboratories around the world have designed ingenious experiments to seek them. Sensitive instruments scan for subtle signatures, tiny effects, whispers hidden within noise. The universe often communicates softly, very softly. The surprising observation is that some of the most advanced scientific experiments ever built are designed to detect signals so faint that a single false event can demand months of investigation. Astronomy sometimes feels grand and dramatic. Particle physics often feels patient. Extremely patient. You continue forward. The stars of the Milky Way stretch around you in a luminous band. Invisible dark matter is thought to permeate the galaxy, extending far beyond its visible disk. Yet every attempt to identify the responsible particle leads to new complications. New possibilities emerge. Sterile neutrinos, primordial black holes, exotic fields, entire families of hypothetical particles. The list continues to evolve. Importantly, scientists distinguish between evidence and speculation. The gravitational effects attributed to dark matter are supported by extensive observations. The specific identity of dark matter remains unknown. That distinction matters. One question appears strongly grounded. The other remains open. You pass through a region of interstellar space where stars shine sparsely against the darkness. Here, it becomes easier to appreciate how little of the universe is actually understood. Modern physics explains an astonishing range of phenomena. Nuclear reactions inside stars. planetary motion, electromagnetism, quantum behavior, black holes, galaxies, and yet the dominant matter component of the cosmos still lacks a confirmed explanation. Imagine opening a book and discovering that most of the pages are written in a language nobody can read. That is, in some ways, the current situation. The universe has provided the text. Humanity is still deciphering the alphabet. You think back to the galaxy from the beginning of tonight's journey. The spinning stars, the hidden mass, the invisible halo. All of it depends on a mystery that remains unresolved. And then another possibility arises. What if dark matter is not a particle at all? Some researchers have explored alternatives involving modifications to gravity itself. Perhaps the laws governing gravitational behavior differ under certain conditions. Perhaps what appears to be missing matter reflects an incomplete understanding of gravity. These ideas have achieved varying degrees of success in explaining specific observations. Yet most face challenges when attempting to account for the full range of evidence. The debate continues. Science advances not by certainty alone, but through rigorous testing of competing explanations. The best ideas survive because reality permits them to survive. The weaker ideas eventually encounter observations they cannot explain. The process is slow, sometimes frustrating, often beautiful, because every failed hypothesis teaches something new. Ahead, the stars begin thinning once more. The darkness deepens, and another realization emerges. Suppose humanity eventually discovers the particle responsible for dark matter. Suppose the mystery of invisible mass is solved. Would that complete the story? Perhaps not, because dark matter is only one component of the invisible universe. There is something else, something even stranger, something that appears to influence the expansion of the cosmos itself. A phenomenon so mysterious that scientists gave it a name which essentially translates to, "We know something is happening, but we do not yet know what." Dark energy. If dark matter revealed that most cosmic mass is hidden, dark energy suggests that the very evolution of the universe may be governed by an even deeper unknown. And compared to that mystery, tonight's journey may only be beginning. The Milky Way slowly rotates beneath you. Its spiral arms glow softly across the darkness, a river of stars winding through the night. Somewhere within that vast disk, on a small planet orbiting an ordinary star, scientists continue searching for dark matter. But now another mystery begins to emerge from the shadows. A mystery so unexpected that when evidence first appeared, many astronomers assumed something had gone wrong. The universe itself seemed to be behaving incorrectly. Or perhaps more accurately, it was behaving in a way nobody anticipated. You leave the galaxy behind and travel outward once more. The distances become immense. Galaxies shrink into scattered points. Clusters appear like faint gatherings of light. The cosmic web stretches across unimaginable expanses. Everything continues expanding. This much has been known for nearly a century. One of the greatest discoveries in modern astronomy was the realization that the universe is not static. Space itself expands. Galaxies, on average, move farther apart over time. This expansion traces back to the hot, dense beginnings of the cosmos. The observation transformed humanity's understanding of existence. The universe had a history, a beginning, an evolution. Yet for many years, astronomers expected gravity to act as a kind of cosmic brake. The universe might continue expanding forever, or perhaps eventually slow enough to reverse into collapse. Different possibilities existed. But gravity should oppose expansion. That seemed straightforward. After all, gravity pulls. That is what gravity does. It is practically written into its job description. Then came the surprise. The expansion was not slowing down. It was speeding up. You drift through the vast darkness between clusters. Everywhere, galaxies recede from one another. Not because they are flying through space like shrapnel from an explosion, but because space itself expands. The distinction matters. Galaxies can remain gravitationally bound locally while the larger cosmic fabric stretches. And somehow that stretching appears to be accelerating. An established scientific fact is that observations of distant supernovae revealed that the expansion of the universe is accelerating. This discovery shocked the scientific community. Imagine throwing a ball upward and watching it accelerate away instead of slowing down. Your first assumption would probably involve checking whether gravity had taken a vacation. The cosmos seemed to be presenting a similar puzzle. Something was overcoming gravity on the largest scales. Something was pushing cosmic expansion faster. Scientists needed a name. They chose dark energy. The term does not explain the phenomenon. It labels it. That distinction is important. Dark energy is not a complete answer. It is a placeholder for a profound mystery. You continue drifting through expanding space. The universe around you feels increasingly strange. Earlier tonight, you learned that visible matter appears to represent only a minority of cosmic mass. Now you encounter evidence that another unknown component dominates the universe's energy budget. The surprising observation is that ordinary matter, the stars, planets, gas clouds, black holes, and everything familiar, constitutes only a small fraction of the universe's total contents. The cosmos is largely governed by things we do not yet fully understand. That realization carries a peculiar emotional weight. Humanity often imagines itself standing at the center of knowledge, slowly illuminating darkness. Yet modern cosmology suggests that the largest ingredients of reality remain mysterious. Not because scientists are careless, not because research has failed, but because the universe is genuinely difficult. You watch distant galaxies recede across billions of light years. The farther away they are, the farther back in time you see them. Astronomy is also archaeology. Every observation becomes a glimpse into history. The deeper you look, the younger the universe appears. And somewhere within that history lies another mystery. Dark matter appears essential for cosmic structure formation. Dark energy influences cosmic expansion. Yet both remain unexplained. The two dominant invisible components of the universe are still largely unknown. That is a remarkable situation. Imagine understanding every detail of a ship's paint while remaining uncertain about most of the vessel beneath the waterline. You know a great deal. You also know how much remains hidden. As you continue forward, the observable universe stretches around you. The cosmic web glows faintly. Galaxies cluster along filaments. Voids yawn between them. And questions multiply. What exactly is dark energy? Is it a property of empty space itself? Does it arise from quantum processes? Could it indicate that our understanding of gravity is incomplete? Scientists investigate all these possibilities and more. At present, no definitive answer exists. The mystery remains open, and the consequences are enormous, because the fate of the universe may depend upon it. You imagine billions upon billions of years passing. Galaxies continue evolving. Stars form and die. Black holes grow. Meanwhile, cosmic expansion proceeds. If acceleration continues indefinitely, distant galaxies will eventually disappear beyond observational reach. Future civilizations, if any exist, might see a far emptier universe than the one visible today. The great cosmic web could slowly fade from view, not because it vanishes, because expansion carries its distant regions beyond observation. The thought feels strangely lonely. The cosmos becoming quieter, darker, more isolated. Yet other possibilities exist. Dark energy might change over time. Unknown physics could alter cosmic evolution. Future discoveries may reveal entirely new scenarios. The story remains unfinished. You drift onward through the darkness. The stars become sparse, the galaxies more distant, and the universe itself begins to feel less like a collection of objects and more like a question written across billions of light years. A question involving matter, energy, gravity, time, and existence itself. And ahead, the mystery expands even further. Because if dark matter and dark energy already challenge understanding, some theories suggest that reality may possess hidden dimensions, multiple universes, or structures forever beyond direct observation. The frontier of knowledge stretches onward. And beyond that frontier lies territory where observation gives way to possibility, where science remains careful, where speculation begins, and where some of the strangest ideas ever conceived await in the darkness ahead. The galaxies continue to drift apart. Around you, the observable universe stretches across distances so vast that language begins to lose its grip. Light years become millions of light years. Millions become billions. Even the largest structures seem small against the backdrop of cosmic time. You have followed dark matter through galaxies and clusters. You have watched dark energy influence the expansion of space itself. Now you approach a boundary, not a physical boundary, but an intellectual one. Beyond this point, observations grow thinner. Certainty becomes rarer. Theories become more ambitious. This is the frontier where scientists carefully distinguish what is known from what might be possible. You float near the edge of the observable universe. Not an actual edge, of course. The observable universe has a horizon because light has had only a finite amount of time to reach us since the beginning of cosmic expansion. Beyond that horizon, space may continue indefinitely. Or perhaps not. No one currently knows. The darkness ahead contains regions forever hidden from direct observation. And that simple fact is astonishing. An established scientific fact is that there are parts of the universe from which light has not had enough time to reach us since the beginning of cosmic history. In other words, there are places we cannot see, not because our telescopes are too weak, but because the universe itself limits what information can arrive. A cosmic curtain exists, and behind it may lie realities forever inaccessible. The thought feels both frustrating and beautiful. Human curiosity naturally wants to know what lies beyond every horizon. The universe occasionally responds with silence. You drift farther into this conceptual frontier. One of the first ideas awaiting you is cosmic inflation. According to a widely supported theory, the very early universe underwent an extraordinary burst of expansion shortly after its birth. For an unimaginably brief moment, space itself expanded at an astonishing rate. Tiny quantum fluctuations were stretched across enormous scales. Those fluctuations may later have become the seeds of galaxies and cosmic structure. The surprising observation is that patterns seen in the cosmic microwave background, the faint afterglow of the early universe, match many predictions of inflation remarkably well. Yet important questions remain. What caused inflation? What mechanism drove it? Why did it begin? Why did it stop? Scientists possess compelling evidence that something like inflation occurred. The deeper explanation remains uncertain. You imagine the infant universe. Not stars. Not galaxies. Not planets. Only a rapidly expanding sea of energy and possibility. Every galaxy you have seen tonight may trace its origins to tiny fluctuations present during those earliest moments. The entire visible cosmos emerging from subtle variations in an almost unimaginably young universe. It is a breathtaking idea, yet it leads naturally to something even stranger. Some versions of inflation suggest that expansion may not have ended everywhere. Perhaps certain regions stopped inflating and formed universes like ours. Other regions continued, and still others evolved differently. This possibility contributes to discussions of the multiverse. Now it is important to slow down. The multiverse remains speculative. Unlike dark matter or cosmic expansion, there is currently no direct observational evidence proving that multiple universes exist. Scientists explore such ideas because some theoretical frameworks allow them. Possibility is not proof. Curiosity is not confirmation. The distinction matters. Still, the concept captures imagination for a reason. You picture countless cosmic domains beyond observation, each potentially governed by different conditions, different histories, perhaps even different physical constants. Whether such realms exist remains unknown. Yet the question itself reveals how far cosmology has expanded. Humanity no longer asks only what lies beyond the next mountain or ocean. It asks what lies beyond the observable universe itself. And sometimes the answers become wonderfully strange. You continue drifting. Another possibility appears ahead. Hidden dimensions. Modern physics describes 3 familiar dimensions of space and 1 dimension of time. Yet some theoretical models propose additional dimensions beyond ordinary perception. These dimensions, if they exist, might be compact, hidden, or otherwise difficult to detect. Imagine a garden hose viewed from a great distance. It appears one-dimensional, like a line. Up close, another dimension becomes visible around its circumference. The analogy is imperfect, but it offers a glimpse of how additional dimensions might remain concealed. At present, however, no experimental evidence has confirmed their existence. The mystery remains open. And then there are wormholes. Few concepts ignite imagination quite like wormholes. Solutions to Einstein's equations suggest that shortcuts through spacetime may be mathematically possible under certain conditions. In popular culture, wormholes often function as convenient transportation systems. Reality is less cooperative. Scientists do not currently know whether traversable wormholes exist. Many proposed models require exotic conditions that may be physically unattainable. Yet the idea persists because spacetime itself appears more flexible than everyday experience suggests. Black holes bend it. Gravity shapes it. The geometry of the universe can be surprisingly strange. You remember the supermassive black hole from earlier. The warped starlight. The distorted clocks. The event horizon hiding unknown physics. In some ways, black holes serve as reminders that nature often exceeds intuition. The universe is under no obligation to conform to human expectations. You drift onward. The darkness grows deeper. Not empty. Potential. Filled with unanswered questions. The unresolved mystery here is perhaps the largest of all. Does reality extend far beyond what observation currently allows us to know? No one can answer with certainty. Perhaps future discoveries will illuminate these regions. Perhaps some questions will remain permanently beyond reach. Science does not promise complete knowledge. It promises a method for approaching truth as carefully as possible. And sometimes that method reveals not only answers, but new horizons. Ahead lies an even quieter territory. Not the physics of dark matter, not the mechanics of black holes, but the meaning of these mysteries, the questions that emerge when knowledge encounters its limits, the questions about time, existence, understanding, and the curious role of conscious observers in a universe that remains only partially known. And there the journey slows. The darkness ahead feels different. Not because the stars have disappeared, not because the galaxies have faded. They are still there, scattered across the immense reaches of space. The difference is subtler. Until now, you have traveled through mysteries that physics can describe, even when it cannot fully explain them. Dark matter influences galaxies. Dark energy affects expansion. Black holes bend spacetime. Cosmic inflation may have shaped the early universe. These mysteries belong to science. Yet as your journey continues, another kind of question begins to emerge. Not what the universe does, but what the universe means. You drift quietly between galaxies. The distances are so vast that entire civilizations could rise and vanish during the time it takes light to cross them. Stars are born. Stars die. Black holes grow. Galaxies collide. The cosmic story unfolds over billions of years. And somehow, within this immense process, conscious beings appear. Tiny observers capable of wondering about it all. That alone is remarkable. You are made of atoms forged inside ancient stars. The calcium in your bones, the oxygen you breathe, the iron in your blood, all trace their origins to stellar furnaces that existed long before Earth formed. An established scientific fact is that many of the heavier elements essential for life were created inside stars and distributed through space by stellar evolution and explosive events. In a very literal sense, the universe learned how to build complexity. Stars created elements. Planets formed. Chemistry grew more intricate. Eventually, somewhere in that long chain of events, matter began asking questions about itself. The thought is difficult to ignore. You float in silence. Around you, galaxies shimmer like distant lanterns. The cosmic web stretches beyond sight. Invisible dark matter continues exerting its influence. Dark energy continues shaping expansion. And yet here you are, contemplating it. Why? Why should a universe governed by physical laws produce creatures capable of curiosity? Science can describe many mechanisms involved. Evolution explains how complexity develops through natural processes. Neuroscience studies consciousness and cognition. Physics describes matter and energy. But deeper philosophical questions remain open. Not because science has failed, because some questions may extend beyond straightforward measurement. The surprising observation is that the universe appears comprehensible at all. Human brains evolved for survival on a small planet. They were not designed to understand black holes, quantum fields, or the geometry of spacetime. Yet mathematics developed by those brains can accurately describe distant galaxies and events billions of years in the past. That is astonishing. Imagine a fish discovering equations that explain the ocean. The success of human understanding remains one of the most extraordinary features of the scientific story. You continue drifting. time becomes the next mystery. Earlier tonight, you encountered relativity near a black hole. There, time slowed relative to distant observers. The experience challenged ordinary intuition. But what is time itself? Physics describes how time behaves. Its relationship to motion, its connection to gravity, its role within spacetime. Yet the deeper nature of time remains debated. Is time fundamental? Or does it emerge from more basic processes? Why does it appear to flow in one direction? Why do you remember the past but not the future? These questions remain active areas of inquiry. The universe provides clues, not final answers. Ahead, a distant galaxy cluster glows faintly. Its light began traveling long before humans existed. You are observing ancient history directly. Astronomy routinely performs what would otherwise seem impossible. Looking into the past. Every telescope becomes a time machine. The farther you look, the older the light. Eventually, observations approach the earliest observable epochs of cosmic history. And beyond that, the mystery deepens. You remember the invisible mass from the beginning of tonight's journey. The missing weight of galaxies. At first, it seemed like a technical problem. A discrepancy in measurements. Now it feels larger. Dark matter became a symbol of something broader. The realization that reality may contain vast hidden components beyond immediate perception. This pattern appears repeatedly. Ancient people believed Earth occupied the center of creation. Later discoveries expanded the cosmos. The Milky Way became one galaxy among many. Visible matter became only a fraction of total cosmic content. Every major expansion of knowledge has also expanded awareness of ignorance. The more humanity learns, the larger the unknown often appears. Oddly enough, this is not discouraging. It is inspiring, because mystery is not merely a gap in understanding. Mystery is what drives exploration. Without unanswered questions, science would have nowhere to go. You drift through the darkness. Stars flicker. Galaxies rotate. Black holes wait silently in distant centers. Quantum particles appear and vanish according to rules that still challenge intuition. Reality continues unfolding whether anyone understands it completely or not. And perhaps complete understanding is not the point. Perhaps the value lies in the search itself. In observation. In curiosity. In the willingness to follow evidence wherever it leads. The unresolved mystery of this section may be the oldest one humanity has ever asked. Can reality ever be fully understood? Perhaps someday dark matter will be identified. Perhaps dark energy will be explained. Perhaps quantum gravity will unite currently separate theories. Yet new questions will almost certainly emerge. Every answer becomes a doorway. Every discovery reveals additional territory. Knowledge expands. So does mystery. You glance once more toward the distant galaxies. They seem both familiar and impossibly remote. The universe no longer feels like a machine waiting to be solved. It feels like an ongoing conversation. A dialogue between observation and wonder. Between certainty and uncertainty. Between light and darkness. And as your journey nears its end, you return to the original question. The invisible universe. The hidden mass. The unseen structures guiding galaxies through the night. After everything you have witnessed, that mystery remains. Perhaps clearer than before. And perhaps deeper than ever. Ahead waits one final stretch of darkness, where the stars, black holes, galaxies, quantum particles, and cosmic ages of the universe will gather one last time beneath the quiet glow of unanswered questions. You drift once more through the great darkness between galaxies. The journey has carried you across immense scales. You have followed the hidden gravity-shaping spinning galaxies. You have crossed clusters bound together by unseen mass. You have traced the vast filaments of the cosmic web. You have hovered beside black holes, watched space-time bend, and ventured toward horizons beyond observation. And now, almost imperceptibly, you arrive where you began. The mystery remains. Ahead, a spiral galaxy slowly turns. Its stars glow softly against the black, just as they did at the beginning of tonight's journey, just as they have for millions of years, and just as they will continue doing long after any single observer is gone. You watch the galaxy rotate. The outer stars still move too quickly. The invisible mass still surrounds it. Dark matter remains hidden. Despite decades of investigation, despite extraordinary advances in astronomy, particle physics, and cosmology, humanity has not yet uncovered its true nature. The footprints remain. The traveler who left them remains unknown. An established scientific fact is that multiple independent observations continue to support the existence of unseen mass influencing the structure and motion of the universe. The evidence persists. The explanation remains incomplete. And perhaps that is fitting. The universe has always revealed itself gradually. Every generation inherits mysteries from the one before it. Ancient skywatchers wondered about wandering planets. Later astronomers discovered galaxies. 20th-century physicists uncovered relativity and quantum mechanics. Modern cosmologists investigate dark matter and dark energy. Each era solves puzzles. Each era discovers larger ones waiting behind them. You float quietly beside the galaxy. Its light reaches into the darkness like a lighthouse shining across a cosmic sea. Far away, other galaxies answer with their own faint glow. Billions upon billions of them, each embedded within hidden structures, each participating in a story still being written. The surprising observation is that the visible universe, the stars and galaxies that dominate human imagination, may represent only a small fraction of reality's total contents. The darkness is not merely empty space. It is active, influential, fundamental. Something unseen helps shape the architecture of the cosmos. Yet the deeper you look, the more profound the mystery becomes. Dark matter is hidden. Dark energy is hidden. The interiors of black holes remain hidden. The earliest moments of cosmic history remain partly hidden. Even the ultimate fate of the universe remains uncertain. Humanity stands in an unusual position. Never before has so much been understood. Never before has so much remained unknown. You continue drifting. The galaxy slowly shrinks behind you. Ahead stretches the larger universe. Clusters, filaments, voids, ancient light crossing billions of years, invisible matter exerting silent influence, expansion continuing across cosmic time. The story remains unfinished. Some future discovery may reveal the particle responsible for dark matter. Or perhaps the solution will emerge from a deeper understanding of gravity. Maybe entirely new physics awaits. Maybe the answer will surprise everyone. History suggests that the universe enjoys surprises. It rarely chooses the simplest path. And so the mystery stays alive. Not because science lacks power. Because reality is vast. Far larger than any single theory, far older than any civilization, far stranger than intuition often expects. You look outward one final time. The observable universe surrounds you like an ocean of scattered fire. Stars burn. Galaxies rotate. Black holes wait in silence. Invisible structures guide cosmic evolution. And somewhere within this immense tapestry, tiny conscious beings continue asking questions. Perhaps that is one of the most beautiful parts of the story. The universe produced creatures capable of wondering about the universe. Creatures who build telescopes, write equations, launch observatories, imagine impossible distances, and refuse to stop searching. The darkness does not feel threatening now, only deep, ancient, patient, a place where answers and mysteries coexist, a place where knowledge grows without ever reaching a final edge. You continue drifting. The stars become softer, the galaxies more distant. The vast machinery of cosmic evolution settles into a slow, gentle rhythm, and the journey begins its final fade into silence. For a while, simply watch. Watch the stars. Some are young and brilliant. Some are old and fading. Each carries a story measured not in years but in millions or billions of years. Entire civilizations could rise and disappear beneath the steady glow of a single star. Watch the galaxies. Spiral galaxies turning gracefully through the darkness. Elliptical galaxies glowing with ancient light. Clusters gathering by gravity's patient hand. Every galaxy a city of stars. Every city part of a larger cosmic network. Watch the black holes. Invisible centers hidden within many galaxies. Silent architects of extreme gravity. Guardians of unanswered questions. Their event horizons remain among the strangest boundaries known to science, where the familiar rules of reality begin to blur. Watch the quantum particles. Tiny fluctuations appearing and disappearing. Fields interacting throughout space. The microscopic world quietly supporting the grand structures of the cosmos. The largest galaxies and the smallest particles are chapters within the same story. A story still being explored. And watch cosmic time. The slow unfolding of billions of years. Stars igniting. Elements forming. Planets emerging. Life appearing. Questions being asked. Time carrying everything forward through an ever-changing universe. The cosmos continues whether anyone observes it or not. Yet observation adds something special. Awareness. Wonder. The ability to look outward and recognize how extraordinary existence truly is. Perhaps dark matter will one day be understood. Perhaps dark energy will reveal its nature. Perhaps black holes will surrender their deepest secrets. Or perhaps every answer will reveal deeper layers waiting beyond. Either way, the search continues. The stars continue shining. The galaxies continue turning. Quantum particles continue dancing through the fabric of reality. Black holes continue keeping their silent watch. And cosmic time continues flowing across the immeasurable depths of the universe. You drift peacefully among them all, suspended between knowledge and mystery, between what is known and what remains hidden, understanding far more than your ancestors ever could, yet still standing before secrets that have not revealed themselves. The invisible universe remains, quiet, patient, waiting, and somewhere in that immense darkness, the next discovery already exists, unseen, awaiting the moment when curious minds finally learn where to look.